Our next presenter is Maria Strack from the Department of Geography and Environmental Management at the University of Waterloo. Maria, Canada Research Chair in Ecosystems and Climate, leads an internationally recognized research program investigating greenhouse exchange in peatland ecosystems, the world's largest natural terrestrial carbon stores. This work includes participation in some of the first peatland reclamation projects in Alberta's oil sands. She works closely with industry, government, and non-governmental organizations to translate her findings into improved land management and in the face of climate change.
Thank you. I'm Maria Strack from the University of Waterloo in the Department of Geography and Environmental Management. And I'm pleased to be here this evening to talk to you about peatlands, also often referred to as bogs, fens, or muskeg. These are wetland ecosystems that have stored large amounts of organic matter in their soil. So in fact, plants in peatlands are really growing on the dead bodies of their former selves. As places where carbon is stored in plants and soils, peatlands, as well as other ecosystems, can be managed in a way that to act as natural climate solutions. And this simply means we try to take advantage of the ability of ecosystems to mitigate climate change. And while it doesn't replace the need to rapidly reduce our reliance on fossil fuels, it's been estimated that natural climate solutions represent more than a third of the affordable climate mitigation strategies needed in the next decade. Peatlands are such globally important aspects of this strategy that the United Nations Environment Programme has developed the Global Peatland Initiative with the goal to protect the valuable carbon stock and keep it out of the atmosphere. And in Canada, we're extraordinarily blessed with peatland ecosystems. They cover at least 12% of our land area. We have more than a quarter of all the global peatlands here in Canada, and they represent a stock of about 150 to 160 billion tons of carbon stored in soil, an amount equivalent to over 750 years of our current rate of anthropogenic greenhouse gas emissions. So it's clear that peatlands are a vast carbon storehouse, and although they are exchanging other greenhouse gases with the atmosphere, modeling has shown that by taking carbon dioxide out of the atmosphere and storing it in their soil for thousands of years, they represent a net negative radiative forcing, or in effect, a cooling of the atmosphere. And in addition to that greenhouse gas removal, the types of plants that grow in peatlands and the wet surface conditions have also recently been shown by Helbig and colleagues to lead to a net cooling of about 2 to 3 degrees relative to adjacent forests. So from a climate change mitigation perspective, there are many reasons that we want to keep these ecosystems on the landscape. But unfortunately, they also face many threats. Some of these threats are related to ongoing climate change, including thawing of permafrost or changes in fire frequency and severity. But what I want to focus on today are direct anthropogenic disturbances on the landscape. This includes things like drainage, peat extraction, removal of peatlands to mine other resources that are under the ground, creation of transportation corridors, and all of these alter the ability of ecosystems to store carbon and exchange greenhouse gases. But they also represent opportunities where we can develop management strategies that reduce these emissions and protect stored carbon. So when we consider climate-friendly land management strategies, one option is to reduce disturbances that we know will turn these peatlands from carbon sinks to carbon sources, thereby avoiding those greenhouse gas emissions. Or we could work to restore degraded ecosystems and turn them back into carbon sinks, effectively pulling greenhouse gases out of the atmosphere. And so we've worked to compile data to estimate the potential of these peatland natural climate solutions in Canada. And we've come up with a number of about 10 megatons of carbon dioxide equivalents per year in the year 2030, or just over 1% of Canada's current anthropogenic greenhouse gas emissions. But what we can see is that the uncertainty on that value is very large. And in fact, peatlands might represent a very substantial opportunity for greenhouse gas emission reductions. So for the rest of my time, I want to focus on a few case studies to talk about where that uncertainty comes from and why we may be able to constrain it better in some cases, like peat extraction in the green box there. So in order to calculate this natural climate solution potential, we need to know where peatlands are, the rate at which they're being disturbed, and what happens to carbon and greenhouse gas emissions once they are disturbed. And unfortunately, despite mapping efforts to improve Canada's peatland inventory, the data gaps in all of these areas are substantial. But if we consider the case of peat extraction, we actually understand the situation fairly well. And this is because we've had a close, nearly 30-year partnership with peat producers through the Canadian Sphagnum Peat Moss Association, so that we now know well where activities are happening on the landscape, both in terms of extraction and restoration as pictured in the map. In addition, this research partnership has led to the development of very effective restoration techniques for which we also understand well the outcomes and what they'll be. And here you can see an extracted peatland transitioning to a restored site and me holding the peat that's accumulated after 20 years. And this research program has also allowed for the quantification of greenhouse gas emissions through that restoration trajectory, so that we also know well the benefits that we get from a greenhouse gas perspective from restoring sites, shown in the blue lines here, versus not restoring them in black. And we know that we can turn these systems back into carbon sinks within about 20 years. But for many other disturbances, we have much more uncertainty, and a good example of this are seismic lines. Seismic lines are simply long linear clearings across the boreal forests that have been used for geologic exploration, in most cases for mapping oil deposits. And part of the problem is that we don't know well where these lines are on the landscape. Even in Alberta, where there's fairly detailed maps of these disturbances, many are missing. And in the map on the right, all of the red lines are those that did not occur in the provincial database. So already we can see that we have a problem with just knowing where they are and the rate that this disturbance is occurring. But probably more importantly is that we don't know what happens in terms of carbon storage in peatlands when they're disturbed by seismic lines. And this is now an important focus of our research program. While we can see clearly that there's a change in the vegetation cover, we're working in the field to quantify what this translates into for carbon and greenhouse gas exchange. And this is important because currently there are active restoration programs working to grow trees back on these lines across peatlands. But without understanding the effect of various management strategies on peatland carbon storage, the climate impact of these restoration strategies cannot be included in decision-making. And this is really the overall aim of our research program. As we face the climate crisis, we work with multi-sectoral partners in order to collect the required data that we need to develop the management strategies that will best allow us to harness the natural carbon capture and storage service that our Canadian peatlands provide. Thank you.